Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In my previous lecture, we were discussing about the discrete word representations. We have discussed about the bag of words, the one-hot encoding and TF-IDF ways or TF-IDF models for discrete word representations. Today we will continue a little bit with the discrete word representations and then we will go into distributed word representations. So, the contents for today's session looks like discrete text representations. In that one we will discuss about n-gram models, then introduction to distributed word representations. In that one we will discuss about word-to-vec, skip-gram model and continuous bag of words. Now, we will see what is this n-grams. N-gram language model predicts the probability of the next word given n-1 previous words. What do I mean? We mean that the probability or the sequence in a sentence, the words come in a sequence. The probability of a word coming in the nth place depend on the n-1 words that are there in that sequence. Now, in this n-grams, I will introduce you all with some new terms like unigram, which means where we take n equal to 1. Then there is bigram where n equal to 2 and we have trigrams which are n equal to 3. Now, I will explain what exactly is the meaning of unigram, bigram and trigram. So, suppose I have the sentence, I love natural language processing. If I take one word at a time, like I separate word, love separate word, natural separate word, language separate word and processing separate word, we call them as unigrams. Okay. Similarly, when we take two words at a stretch, like I love, love natural, natural language, language processing, then we call each of them, like I love is a bigram, love natural is a bigram, like this. Okay. Then we have trigrams where there are three words which are taken together, like I love natural language, natural language processing. That means three words are taken together. So, each of these one I love natural, this entire thing is a trigram. Okay. Now, natural language is not a collection of words. Natural language is not a collection of words. What do I mean by that? Suppose I have a sentence, the cat sat on the mat. Now, if I change the sequence of the words there, the cat sat on the mat is the first sentence, the mat sat on the cat, the sat mat on the cat, sat the mat on the cat. So, what we are getting, are the meaning of all these sentences same? No, they are not. That means, it is not a collection of words. The order at which the words come one after the other, that gives the meaning of the sentence. Okay. So, all these sentences other than the first one, the cat sat on the mat, doesn't, the other four sentences, the mat sat on the cat, the sat mat on the cat and the sat the mat on the cat, they doesn't have a meaningful sentence. Okay. Now, language modeling assigns probabilities to a sequence of words. So, which word will come after which word? There is a probability that is assigned by language model. That is the main task of a language model. That means, which word will come after which word. Okay. That is the main task of any language model. The cat sat on the mat, this has a high probability score, whereas the sat mat on the cat, that has a low probability score. So, language model will predict with a high probability score that the cat sat on the mat, this sequence is having high probability. That means, it is giving some meaning, it is some information is being passed through this sentence, whereas the sat mat on the cat, it has a low probability score because there is no meaning associated with this sentences, this chunk of words. Now, we will see something called as Markov's assumptions and which is used in language modeling. So, we will understand what is this Markov's assumption and how language modeling, Markov's assumptions are used. Same example we take, the cat sat on the mat. Now, we will first look into first order Markov's assumption. First order Markov's assumption is basically a bigram model. So, what exactly it is? It assumes the probability of the next words depend only on the previous one. Okay. So, here is the equation for that one, we will see. So, this means the probability of the word T given your previous words or the context words are from 1 to T minus 1. Okay. So, this is a conditional probability. The probability word WT will come after WT minus 1 depends on all the words that are there from T equal to 1 to T equal to T minus 1. Okay. So, from the cat sat on the mat, the probability that mat will come after the depends on all the words that are there from the first instance, that means the cat sat on the. Okay. So, this is, you know, if I want to get the probability, it can be, you know, it can be approximated to the probability that the word WT will come given WT minus 1. That means, the mat will come only, or the dependency of the word mat will be only on the last word, the. Okay. So, this is called as a bigram model, which means the probability of a word coming in a sequence depends only on the previous word that is present before the word. Okay. So, this is called as Markov's first order Markov's assumption. Okay. Example, we have bigram counts from the training corpus. What is my training corpus? The cat sat on the mat. So, the probability of the word cat given the previous word is the, probability of the word sat coming given the previous word cat. So, it will depend, the probability of the word cat depends only on the previous word the. At the same time, the probability of the word sat coming depends only on the word cat. Okay. The probability of the word coming on depends only on the previous word, which is sat, and so on. Okay. So, first order Markov's assumption tells us that the probability of a word coming in a sequence depends, it does not depend on the entire context, but if we look at the just previous word, it will give, the assumption works, you know, it gives a meaningful output. Okay. Then we come to second order Markov's assumption. What is that one? It is basically a trigram model. It assumes the probability of the next word depends on the previous two words. So, in first order Markov's assumption, we have assumed that the probability of the next word depends on previous one word. Here, probability of the next word depends on the previous two words. So, probability of the word WT depends, which depends on the context, can be approximated as probability of the word WT depending on T minus 1 and T minus 2, T minus 2 and T minus 1. Okay. So, this is second order Markov's assumption. From the sentence, we can extract the trigrams. So, what we do? We had the sentence, the cat sat on the mat. So, if we take a trigram, the trigram will be the cat sat. So, if we want to take the probability of the word sat as the next word, it depends only on the cat. Okay. Probability of on depends on the cat sat. Here, which trigram we have taken? It is cat sat on. Okay. For the third one, sat on the. So, this is the trigram which we have taken, and we are predicting the probability of the word the coming given the previous two words are sat and on. Then probability of mat depends on and the. Now, the models uses the last two words to predict the next word. So, this is second order Markov's assumption. This will be more accurate as more words are taken into context than before. Okay. Example, the cat sat on the mat. Here we have done it from this example. Okay. So, the kth order Markov's assumption. So, after first order, second order, we have a kth order Markov's assumption, where we say the probability of the next word depends on the previous k words. Okay. So, here the probability of the word coming WT coming as the next word depends on the entire context from 1 to t minus 1 can be approximated using Markov's kth order assumption, where it gives probability of this word WT coming as a next word depends on WT minus k to WT minus 1. Okay. So, this k can take any value, it can take 4, 5, 6 any value. Now, for example, with the k value of 4, a 5 gram model, after seeing the cat sat on. So, if we have the sentence the cat sat on the mat, if I take a 5 gram model, the cat sat on, okay, what will be the next word, what will be the fifth word. Okay. So, the cat sat on the, so that the will be predicted based on the cat sat on. Okay. So, that is what is your kth order Markov's assumption giving. Now, there are certain limitations of this Markov's assumption. What are they? Suppose we take this sentence, the animal did not cross the road as it was too wide or tired. Now, we want to see what is the word that will come here, either whether it will come wide or it will come tired. What is the word that gives more sense? Now, if your k is 4, that means 1, 2, 3, 4, it is not even going to the word road. K equal to 5, so 1, 2, 3, 4, 5. So, this road is coming into picture, but we are missing the term animal, missing the word animal. The animal did not cross the road. There can be two versions, right? The animal did not cross the road as it was too wide. What is wide? The wide refers to the word road, but if it is tired, it refers to the word animal. Okay. So, we may miss taking the animal word into consideration if k value is not so large. Okay. Capturing long term dependency of on the value of long term dependency depends on the value of the k chosen. Okay. Now, so we need a language model which will consider all kinds of features of the context which might be useful in predicting the word. So, we have to take the long term dependency of the words in the sentence as well. Okay. So, that is where Markov's assumptions have a limitation. Then we come to something called as the distributed text representations. What are these distributed text representations? How they overcome the limitations of discrete text representations, we will see that one. So, distributed text representations is a way of representing a word or a large text unit as a dense vector in a continuous space instead of as sparse indicators like one hot vector. So, we have seen that representing words as a vector we have already seen in discrete one, but there it was in the form of one hot encoding or one hot vectors, but they were sparse vectors. In this case, we will get in distributed text representations we will get dense vectors, and these dense vectors are called as word embeddings. So, we will see what are these word embeddings, how do we get them, what are the properties that are associated with these word embeddings. Okay. So, these word embeddings basically they are a real valued d-dimensional distributed feature vector with each word in the these real valued d-dimensional distributed feature vectors, one vector will be associated with one word in the vocabulary. So, each word in the vocabulary will get one vector which is having a dimension d dimension, and it is a real valued vector. Okay. Now, what are the properties of this vector? These vectors are d dimensional, where d is much less than absolute value of v being the size of the vocabulary. That means, if your vocabulary is having say 10,000 words, then the vectors, usually these word embeddings are of dimension 100, 200, 300 dimension, which are much less than the total number of words that are present in your vocabulary. Okay. And the most important property of these vectors are similar words occur together and have similar context. So, if we see the vectors placements in the vector space, we will see that the similar words are having very closely spaced vectors, and dissimilar words are separated out. Okay. You see, we have 3 vectors v rose, that means the word embedding for the term rose, then marigold, v marigold, and v cat. If you see, these numbers are representative. If you see, just to show that how they are very similar in case of similar words or words having similar context. If you see this number 1.6, 1.4, 2, 2.1, -5, -5.2, 4, 4.3. So, these are very nearby numbers, whereas v cat is not in the group of flowers. Okay. Rose and marigold falls in the group of flowers. So, cat is having the number 7.4, -0.1, -1.1. These numbers are representative, just to explain that different words of different context can they are spaced apart, whereas words of the same context, they are close by. Okay. So, in distributed text representation, it goes like this: you shall know a word by the company it keeps. It is a quote by J.R. Firth in 1957, which means the meaning of the word will be very similar to the words that are placed in the vicinity of that word. So, you shall know a word whether the word is of which context, it will be very much given by the neighboring words. Okay. Now, we will see. So, as I was telling, the core idea of distributed text representations are similar words tend to occur together and will have similar context. Now, can the calculations using these vectors capture semantic association? We will see whether the meaning associations are captured using these vectors. We have to see that one. Now, just see this image. These are the vectors of certain words. I have taken king, queen, man, woman, and king minus man. So, if you see, this is a vector. This vector is for the word king. This vector is for the word queen. This vector is for the word man, and this is for woman. If you do use a parallelogram law of vector addition, and you see this is the vector for v king minus v man, then v king minus v man plus v woman equal to v queen. How do we get that one? See, v king is your this vector. V king minus v man is your this vector. Okay. This is the vector which is giving the distance between the vector for king and vector for man. Then with this one you add v woman. Where is your woman vector? Here. Okay. So, if you add these two with a parallelogram, you can see this one and this one. Okay. Then the diagonal is your v queen. That means v king minus v man plus v woman equal to v queen. Okay. This is from the vector addition. So, v king minus v man equal to V queen minus V woman. So, from here can I write this one? Yes, I can write this one. From here I can write very much this one, okay, because this is based on my vector addition. Here what do I see? See, king and queen refers to some royal, from a royal family, a person from a royal family. So, the royalty and human aspect are preserved. So, man and woman, these are basically normal human being, where king and queen, they are from royal family. So, king minus man equal to queen minus woman, which means the royalty and human perspective are preserved, only the gender attributes are changed. That means, king has been replaced by queen, man has been replaced by woman. That means, this the context has been preserved, only the gender has been changed. Okay. So, that is the beauty of distributed text representation. Now, we will come to, once we have understood distributed text representation, we will come to something called as word to vec model, which uses this distributed text representations, okay, and which are very much used in NLP. So, what is this word to vec? It is a technique for converting words into numerical vectors or word embeddings that captures semantic relationships, meaning words with similar contexts have similar vectors. Okay. The same thing we are having here also. It is a combination of two techniques, the skipgram model and a continuous bag of words. So, it is a combination, word to vec is a combination of skipgram model and continuous bag of words. Now, we will see what are these two, skipgram model and continuous bag of words. Both of these techniques are shallow neural networks that map words to a target variable, which is also a word, or it can be a sequence of words. Okay. So, we will see when I tell what we will see what I mean by the target variable and how it is a set of words. Okay. We will see in the next slide. Both of these techniques learn weights of the neural network, which act as word vector representation. Okay. So, these word vector representations actually are coming from the learning of the weights in the neural network. Okay. Now, before I go to how this skipgram model and your continuous bag of words model work, we will just learn about the center word and context word in NLP. What do you mean by center word and what is the context words? So, suppose we take the sentence, students enjoy reading books in the library. So, if we see the word reading, it is the center word, okay? And if you take one on the left and one on the right, those are the context words. So, students enjoy reading. So, enjoy is a context word, books is also a context word. Students enjoy reading books in the library. Okay. Now, this is for a window size equal to 1, because I am from the center word I am seeing one word in the left and one word in the right. Now, what will happen if the window size is 2? For the word center word reading, I have students enjoy, that is my context word, and books in, that is my context word. Okay. So, this is for window size 2. Okay. So, students enjoy and books in, both are context words given the window size is 2 for the center word reading. Now, we will see word to vec word embeddings, how they capture the semantic relationship. So, example, I have taken two sentences. The king and the queen rules the kingdom. A man and a woman lead their people. Okay. So, these are two example sentences. Places them in similar context, rule, lead, people. So, these two sentences we can say they are very similar in context. That means, the king and the queen, they rule the kingdom, whereas the man and the woman lead the people. So, king and queen, they are of royal family and they rule the kingdom, whereas man and woman, they are normal human being and they lead a group of people. Okay. So, it is almost very similar context. Now, if we see the word embeddings that are coming from word to vec, you see this image will show that one. We have the vectors for, suppose the placement of the vector here is queen, for queen, woman, king and man. So, these words are placed in this space, they are arranged like this. And if we see, there is an arrow or the direction of from woman to man, this one, sorry, the direction between, just 1 minute. So, the direction between woman and man, this one, is similar to the direction from queen to king. So, queen to king, this is the direction, whereas woman and man also in the same direction, which captures the semantic relationship. So, word to vec word embeddings come in such a way that the semantic relationship is captured. How? The direction of the vectors, by the placement of the vectors, all these things take into consideration the semantic relationship, okay, and that is how it is captured. Now, we take 4 words big, small, biggest, smallest in the vector space. We see how they are placed. So, if we see, this is the vector space x, y, z coordinate, big, biggest, small, smallest. So, these are the placement of the vectors. Now, if we see, the direction represents a relationship. So, big to biggest, okay, small to smallest. So, it captures the relationship big to biggest, small to smallest, okay. And also the arrows have similar length, which means big to biggest, the distance between big and biggest word embeddings is equal to the distance between small and smallest. So, this type of word embeddings come with the word to vec. That means what exactly it is capturing? The vector biggest minus vector big is almost similar to vector smallest minus vector small, okay. That means word to vec has learned a syntactic relationship. What is this syntactic relationship? Anything that is related to grammar is called syntactic. So, base adjective is big here and superlative form is the biggest, okay. So, big and biggest, and in this case the base adjective is small and then the superlative is smallest. So, it has captured the syntactic relationship as well as the directions have shown there is a relationship between big and biggest and small and smallest, okay. Now, we have prediction of center word from context word or context words, okay. What is that one? So, this is called as the continuous bag of words model, we call it as CBOW, okay. What is that one? We will see. So, suppose you have the context words WT minus 2, WT minus 1, WT plus 1 and WT plus 2, and you want to predict the WT word, which is the center word. So, or what will be your inputs, or we will see, we will just take one sentence and example, neural networks dash word representations. So, neural network, neural is WT minus 2, network is WT minus word, this is your WT, word is your WT plus 1 and representation is your WT plus 2, okay. Now, all these are going T minus 1, T minus 2, T minus 1, T plus 1, T plus 2, these are going as your inputs to your neural network, and we want the output to predict the what output do we want? We want the prediction of WT. So, when we give these inputs, what are these VWT minus 2? This is the vector embedding. So, VWT minus 2, VWT minus 1, VWT plus 1 and VWT plus 2. So, these are the vector embeddings which is going into the network, and then what happens here? After going through the network, the hidden layers give me an output H. What is this H? H is equal to, it is the average of all the word embeddings, H equal to 1 by 2 m summation over the V T plus J. What is your J? J runs from minus m to plus m and J not equal to 0. In this case, your m is your 2. So, it will be word embedding V T minus 2 plus v t minus 1 plus v t plus 1 plus v t plus 2. So, all this and then you take the average of that one 1 by 2 m. Okay. And how do we calculate the probability of W t equal to I? What is that? Means at this W t, the word at the tth time instance or tth time step will be equal to I, giving the context words is given by H transpose V I prime divided by summation over all the w's belonging to V exponential of H transpose V w prime, okay, V I prime and V w prime. Okay. Now, what exactly is this one? This is the softmax. It is a softmax. We all know probabilities are given by softmax activation function. So, exponential of H transpose into V I prime divided by summation of exponential H transpose V w prime over all the w's belonging to V. What is this? V I prime is the output embedding of the word I, okay, and this takes V. What is V? Capital V. V is the total number of words in the vocabulary. Now, we will look into prediction of context words from the center word. What is this one? So, this is called as the skipgram model. So, in skipgram model, we have the input as the center word W t, from where we get W t, V w t, which is the word embedding of the vector word embedding for the word W t, and from here we want to find out W t minus 2, t minus 1, t plus 1, W t plus 2. So, these are the outputs that I am asking my model to give me. Now, here H equal to V w t. Okay. So, H is nothing but it is just giving the vector of the vector embedding of the input word. So, the probability of the word t plus j, which is one of the context words, equal to I given the input word W t is equal to exponential H transpose V I prime divided by summation of exponential H transpose V w prime, where W belongs to all the W takes all the values of V. V is my vocabulary. Okay. Now, for each word in the vocabulary, there is an output embedding which is your V w prime. So, that is taken. So, this is also from the softmax activation function, which gives me the probability of a context word given there is the center word is already given, which is equal to exponential H t V I prime divided by summation of exponential H t V w prime. The summation is over all the w's belonging to V. Okay. So, this is the skipgram model. So, with this one I come to the end of the session. I will summarize what we have studied today from the beginning. So, we have started with n-gram models and we have seen what are the unigrams, bigrams, trigrams and how they are used in language modeling, what is Markov's assumptions, first order Markov's assumption, second order and kth order Markov's assumption, what is the limitation of that one. And then we have come to distributed text representations, where we have seen that each text is associated and we get a vector which is a dense vector which represent that word. In the text word, the vector representations we get from the distributed text representations, which capture not only the semantic but also the syntactic relationship between them. So, the placement of these vectors in the vector space, it captures both meaning as well as the syntactic relationship. And then we have seen word to vec model, which is a combination of continuous bag of words and skipgram model. We have seen continuous bag of words, what exactly it does. It takes the context words and gives the predicts the center word, whereas in skipgram model it takes the center word and predicts the context words. So, the probability calculation depends on the softmax. So, it takes the word embeddings from each of the input words. In both the cases, the input words, whatever it is given, the word embeddings then go through the neural network, and then softmax activation function comes into picture, where it is conditional probability. That means given the context words, what will be my center word, or given the center word, what will be my context word. So, we have seen how these center word prediction and context word predictions happen in word to vec model. So, with this one I conclude my session today, and in the next session we will look into the next part of NLP, where we will be talking about another two word embedding algorithms or models. Word to vec is one of them. Another two, we will see glove representations or glove embedding and fast text embedding, which we will see in our next session. So, with that one I conclude today's session. Till we come back with my next session, please keep learning, happy learning, and thank you all.